Okay, the next part is the second effect, which is the longitudinal diffusion, denoted as B. Okay, longitudinal diffusion is whereby if you have a very um, like zone over here, when it goes into the towards the detector, it will start to diffuse in terms of concentration by time. Okay, this is not related directly to the particles itself, but it is more related to how fast or how slow the mobile phase flow. Okay, so at the start it start with like this, slim, narrow, pointy, but at the end of the day, when it goes to detector, okay, it's very broad like this. Okay, this is the ideal band. You want band like this, but if you have band like this, it's going to give you something like this. Okay, so it is a result from tendency of solid to diffuse from a very concentrated center to the more diluted region. Okay, this occur primarily in the mobile phase. Means that why is it occurring in the mobile phase? Because as I mentioned just now, it is depending on the flow rate of the mobile phase. Okay, if you see from the graph over here, this is the B term. I apologize in the previous video and slides, the B and C term is the other way around, but this is the correct one. So the B term over here, you see that the lowest H is occurring at high velocity. Okay, at low velocity over here, the H is very high as compared, this one is high as compared to this one. This is even higher. This H over here is very high as compared to when you have something like this. So means that that's why the equation is B inversely proportional to the velocity. So the higher the velocity, the faster the mobile phase goes, the band broadening because of the longitudinal diffusion is lower, denoted as by the low H. Okay, the low H is the one that we want. Okay, so because of the axial spreading diffusion along the column axis, it will create a band that is broad. Okay, this is inversely proportional as I mentioned just now here, and higher velocity provide less time for diffusion to occur. Okay, so imagine that if you are bringing a bucket of water, right, and the bucket is unfortunately cracked. So if you run faster with the bucket, at the end of the side over there, you have less leakage, means that you have more water. But if you move slowly, you will have more leakage and less water. That's the analogy that I can think of lah. So this is to show you how it is in terms of calculation. Okay, so the sigma just now is the variance, right? Okay, is related to the coefficient of diffusion of analyte in the mobile phase. Sometimes it is presented in table, available in textbook or internet, and the total time of sample in mobile phase. Okay, and here is also having one factor on the nature of packing. Okay, and this is the factor lah, it's already calculated for you guys. So the factor for open tubular is higher a bit than this one. Okay, so dm is also dependent on the temperature and pressure. So if let's say you have GC with a high molecular weight carrier gas, use the longitudinal diffusion is less. Okay, so this is very significant in HPLC and also in GLC, gas liquid chromatography, because in gas liquid chromatography, the GC open tubular, sometimes the flow rate depend will actually result in different broadening. Okay, finite time required for the solid to transfer in and out of the stationary phase. So once it goes into the stationary phase, goes inside here, and then the analyte want to go out again, so that's the factor. So broadening occur when either of this rate is low, okay, and also it depends on the diffusion rate of analyte.